Hello, everyone. We are ME24 working with Otis Elevators, and our project is using SysML and model-based systems engineering with application to a self-climbing autonomous robotic motion platform design. So on the agenda today, we will go over the objectives we had to complete for our project, our solution to this problem, how our solution fulfills the requirements set by Otis, any additional work we need to do before the project is complete, and at the end, we'll do a quick summary. So these are the objectives that we had set by Otis to complete for the project. So the main objective of our project was to develop a thorough understanding of model-based systems engineering principles, learn SysML as well as the best practices associated with the software, and apply this acquired knowledge to a self-climbing elevator system. So we spent the majority of the first semester researching and understanding the fundamentals behind SysML, as well as model-based systems engineering, and spent this semester applying our knowledge to the robotic motion platform. And then on top of this, Otis tasked us with the creation of an archival system for the process for our model, which we will cover later in our presentation.
In SysML, there are 9 diagram types that are used to model the behavior and structure of a system. The diagrams are connected so that values can be stored such that they are consistent throughout the model. Here you can see how a value such as torque is stored in order to calculate power use. Next, we have an activity diagram, which is meant to show the process and behavior of the braking system, ensuring that the elevator behaves according to our requirements. Here are some initial designs we created based on a self-propelled propulsion system. These designs use friction from the wheels to create the motion needed to move the cab up the elevator shaft. As we move forward with the project, we wanted to improve our design. In this design, we focused on maximizing the cab size by having the wheels pinched against an I-beam. As you can see in this design, the only lost space is due to the I-beams.
So along with our ECE counterparts, we spent several weeks calculating the forces in the environment our system would be exposed to and gathering components that supported our system, for example, several motors and the best sensors. Since our elevator was meant to be self-climbing, meaning there's no ropes, again, we selected the I-beam, as seen in the free body diagrams before. On the slide, you can see our calculations we did for the system. For these calculations, we had to account for the 4 main forces that the elevator was exposed to: gravity, acceleration, rolling friction, and aerodynamic drag. Gravity and acceleration being the majority of the forces. Rolling friction was severely low. There's only a small amount of the tires in contact with the steel beam at one point, no matter the size of the tire. And aerodynamic drag is seemingly negligible. Our final trade study in SysML found a power rail to be more efficient than a battery system on the cars based on car mass and energy consumption values. The purpose of the SysML requirements and diagrams is to ultimately run a trade study. The purpose of the trade study is to select several measures of effectiveness and see how different conditions affect performance. For example, we selected 2 motors that operate at different RPM and horsepower values and ran them through our simulation to visualize their power requirements. We also performed this analysis on different tire diameters to measure wear over time. This diagram here is part of the results of our trade study. As you can see by the red box, case number 1 shows the ideal operating conditions of our elevator system since it showcases the lowest power usage overall. It is also important to highlight that the tire diameter for this case is 0.127 meters. With this trade study, we have demonstrated a complete model in SysML that can take our inputs and functions and output effective results.
We are currently finalizing an archival system for the project. The goal of the archival system is to develop naming conventions and libraries that allow for the reuse of past designs. One key benefit of SysML is being able to speed up the design and development process by taking advantage of past work. A good archival system will allow for something such as the power system solution to be easily dropped into a future design.
So in summary, we established a solid foundation of SysML knowledge for modeling our system. We investigated several different system configurations and ran trade studies in SysML. We used free body diagrams and hand calculations as proof of concept for our design. And we're currently finalizing our SysML archival system.